Today we'll be doing a presentation on projections, and specifically projections in South Africa, and the implications, the history to it, some of the background to why we use projections, and some of the things that you need to take into account. So this will be in 3 chapters or 3 sections. We will be recording this, and the idea of this session is to look into things like navigation. How did we come to start using this concept called latitude and longitude? The idea of a geographic coordinate system. What are projections? What are the properties of projections? And what I mean by that is that what are the things that projections are good at? What are the things projections are bad at? And depending on what projection you are using. Finally, what are the South African projections? What ones do we use? And which ones should be used for different scales or different applications, and then some which potentially should be used with circumspect. And then finally, wrap this up. So, the easiest way to explain projections is to take the proverbial orange and draw the earth on it, and say, how are we going to take this orange, and how are we going to flatten it, so that we can print it on a map or put it on a computer screen that you can see things across hemispheres or across from the east to the west and north and south. So here's typically a Gall-Peters projection, which is how you would peel that orange if you could and try and flatten it to make the earth. We all know the Mercator projection, and we'll touch on that a bit later. But this is just a representation of how you could peel your orange, or a very new one, which is very computer-centric, and is something that can only be done with a computer because we have the technology, is something called the Dymasion projection, which will allow you to create this very interesting looking map, sometimes very challenging to understand and interpret, but the bottom line is that's what a projection is. How do we take a round sphere or a body such as an orange and wrap it to be placed on a flat surface or a map, and then maintain properties such as shape, area, distance, and directions, etc. So, when we look at the considerations of projections, it's questions like, what type of scale of data are you mapping? What's the extent of the data? Is it the whole of South Africa, or is it just Pretoria or Johannesburg? And what are you trying to maintain? Is it area? Is it a distance? Is it shape? Is it scale? And see some of the considerations that need to be taken into account when one chooses a prediction for a specific data set. And in this case, as I say at the bottom, if you're mapping at a scale of 1 in 50,000 or less, it has to have a high accuracy requirement. And then we'll use a very different projection than what we will do when we're trying to map areas across South Africa. Some of the other considerations are, what's the shape of the Earth? So when I say that, I mean what shape of the Earth are we using? What area of the world are we mapping in? Because that will depend what definition of the Earth's surface are we using. And then, as I've already said, what are we trying to maintain? Is it area, distance, direction, or shape? And then the concept of some projections they're reversible, but they're only reversible if you use them in a specific format. So don't go moving data between projections and assume that the answer you're going to get when you come back to the original projection is going to be the same. So keep that in mind. Some fun facts or some questions here. You'll never see a north arrow on a full map of America. And the reason for that is that because of true north being above, or even north, true north or magnetic north being above America in the top of Canada, you'll find that the one arrow will point in this direction and the other arrow will point in that direction, all pointing towards the North Pole. So it's just an interesting one. You use gradicules, you will never use a north arrow. And then some examples of why projections are important. In 1999, NATO was active in Belgrade and were bombing Belgrade. And at one point they wanted to bomb a supply depot. But in the definition of the target package versus the physical operation of bombing that supply depot, they used 2 different projections. And the bombs went off and hit the Chinese embassy. And so sometimes projections can be extremely important because there's a loss of life situation at stake if you get them wrong. So understanding projections, knowing exactly what they mean and how you need to use them is important, and making sure you use standard projections which everybody knows about. Then something I learned recently is the concept of that Africa is a very dynamic continent when it comes to the magnetic field. So we have a large drift of magnetic north and magnetic declination across the continent, and this is constantly changing. And that is something that we've got so used to using GPSs and navigating with those. But if you're working with compasses, you still need to understand this, that you can't just assume that the magnetic declination is the same. And I'll give you an example a bit later. So let's start off with navigation. How did this whole concept of making maps and understanding how we measure things and how we place things on the Earth's surface start? Well, if we go back in time, we used stars, and the stars were used to either define north or define south. So in South Africa, we can use the Southern Cross or crux. I'm not going to go into all the details of how you define it, but you look at for the Southern Cross, and you look at the sisters, and you draw these lines, and then where they drop down, that is south. And I'll challenge you all to go and do a bit of a Google on that, and you'll see that you can define south if you can see the Southern Cross. We also can use Orion's belt, and Orion's belt can be seen in both the southern and the northern hemisphere. So in our case, you look for the belt, and where the sword would be on the belt, you can draw a line down, and that will either be north or south, depending on where you are. And sometimes it's good. It's just nice to know. And when you go out into a winter's night and you see, or even summer's night and see clear skies, you can work out where north and south is. So this is something that goes back in time, that we could define north and south using the stars. Over time, and if you look at those dates, 206 BC, the Han dynasty in China had created the first compass. And this is now looking at the magnetic north and not true north, and this is what we'll touch on in that next paragraph. And the Western world started adopting the use of compasses in about 1190. So this is a well-known technology, and I'm sure you've all used those. If we look at, we have an organization under the South African National Space Agency called the Hermanus Magnetic Observatory, and they do many more things, but one of their roles is to define the magnetic declination as it is changing every year, or they report it on a yearly basis. And if you look at the HMO readings at the bottom, you'll see from 1967 we were at 11 degrees west. We then progressed down to 16, but we're now back at 19, or we will be back at 19.2 or 19.4 going to 2024. So this is a constantly moving value of north, and it's something you need to take into account, because if you are doing some navigation, be aware what's true north and magnetic north, so that you aren't making mistakes there. So defining direction, either using the stars or using a compass, is a well-known and well-documented approach to doing this. If you look at measuring distance, how do we measure distance? One way is counting steps. We all roughly know how long our step is, and we can walk along and we can measure out a distance. It's not always that easy. Going uphill, downhill, your step size will change, but the reality is you could get a vaguely decent answer. You've all seen engineers walking around with measuring wheels, and it's a wheel that they roll along the ground, and it counts every time there's a revolution, and that is a way of also measuring distance. You've most likely all heard about the term of knots, and if you're in the sailing community or in the aeronautical community, they use the term knots. And where did that come from? When you're sailing across an ocean and you want to try and work out your speed, you would throw a rope overboard which had knots on at equal distances along the rope. That rope would be joined to a buoy, and you would work out over a period of time how many knots had rolled out from the boat in that time. And that was the concept of a knot. And this has been equated, a knot's roughly 1.8 kilometers an hour. And so the bottom line is that we can use some very simple technology to understand distance or speed, and work back from there if you know the distance. So what are the take-home messages in this idea of navigation? It's very easy to work out direction and distance. We can use the stars, use a compass, and we can count out steps, etc. And this works really well for local navigation. So if I wanted to go from one place to another, maybe 3 or 4 kilometers between them, and I know the direction, I know the distance, and even if I know a distance and I need to turn at an angle or something, I can use that. It works well on a local environment. But if I started to do global circumnavigation, where I wanted to sail from France to America, I need totally new technology. And this is where we'll start talking about this concept of latitude and longitude. And if we look at that there, what is latitude? So latitudes are your southings and northings. And we typically talk about the equator or the Tropic of Capricorn or Tropic of Cancer as being those definitions, in this case 23.5 degrees, or when we go further north into the Arctic Circle and the Antarctic Circle, we have 66.5 degrees. So we know these lines, they're things we were taught at school as part of geography. The catch in that second paragraph is those lines are equidistant. So typically, even at the equator, about 110 kilometers, and at the poles 111. So they're an equal measure across the globe. And this is, in GIS terms, the x-axis. So keep that in mind. And how did we measure these lines of latitude, or how far north or how far south we were? We use a sextant. And a sextant works on the premise that we can see the horizon, we can see a star or a celestial body, such as the moon or the one of the planets, and we can then work at those angles, and that gives us an indication using charts of how far north or how far south we are. The one proviso is you need to be able to see both of the celestial body, so the star or the planet, plus the horizon at the same time. So which means it's typically around sunset or sunrise. So you could not work out your northings or southings when you're in the middle of the day or the middle of the night. If we talk about longitude, and that's typically your eastings and your westings, so that is a moving away from the prime meridian or Greenwich, we have two significant longitudes. The one is the international dateline at 180 degrees, and at 0 degrees we talk about the prime meridian or Greenwich. The intervals here are where the problem comes in, because at the equator, the interval for a longitude is 111 kilometers, but at the poles, it's 0. So it's not an equal measure. So when you are in Cape Town, it's roughly 90, 98, 99 kilometers. At the equator, it's 111. So if you wanted to try and measure something on this round sphere or ellipsoid that we live on, then depending on where you are, you're going to get different answers. And this is where the requirement for a projection which can maintain those properties kicks in. This is typically what we call the x-axis. So it's an interesting one, and something to keep in mind is when we always talk about xy, but we always talk about lat long. And lat long is not xy, that's yx. So keep that in mind. It's sometimes just think about that should we rather be talking about y-x's, or should we be talking about longitude and latitude and not latitude and longitude? When we discuss the idea of how did we measure longitude, latitude's easy. We measure the horizon and one of those celestial bodies, and we get northings and southings. The problem is the Earth is turning, and because the Earth is turning, that every single star will be seen from somewhere in the world or everywhere in the world. Each star crosses the meridian once a day, that last comment. So that means is that we can't look at the height of the star above the horizon as an example, because we need to know the time that we're looking at it. So time influences this estimation of longitude. And the Earth is rotating. We know that 360 degrees in 24 hours, or 4 minutes per 111 kilometers, which means we're moving fairly fast. And we need to understand that. This was a challenge, because when you were sailing from the east to the west, or the west to the east, so you were going from Europe to America, it's very easy to understand how far south or far north you are, but it was very challenging to work out where you were in east and west. And they relied on a lot of dead reckoning. There's a very interesting book, I've given you the front page of it, called Longitude. And one of the biggest challenges of the century was to create a clock that could work on a ship. Because if you think of the old clocks, they were pendulum clocks. A pendulum clock cannot work on a rolling ship. So they had to create clocks that could work on a ship, even if the ship was rolling. And that opened up a whole new set of science into how you build a clock that will work on a rolling ship. And it's a very interesting read. If you ever get the opportunity to go to the Greenwich Museum, they have all these examples of these clocks. But here's an example. if you're out by 4 minutes, you're out by 111 kilometers at the equator. Now, 111 kilometers could be quite a challenge when you're sailing and you're trying to work out where you are, because that's quite a distance. And if any of you have looked at a map, one of the older maps of the world, you will notice, and I'm going to just put on a little circle there, that the map represents the continents in the south and north quite well, but Africa is either very fat or Africa is very thin. And that's because they struggle to measure longitude. So it's always been a challenge. And in this case, this is a map of an area in France, and you'll see that the difference between the 2000 representation of France and the 1693 is not necessarily in north and south. It's in east and west. And so longitude has always been an interesting a challenge, and how do we address that? So when you want to navigate across and move across the world, you needed a couple of things. To measure longitude, you needed a star chart and a chronometer. So you needed a clock that had been calibrated to Greenwich, and a chart which would say, this is what you will see if you're at this time of day in a certain place. And that's what they used to work out the east and west. The latitude, as I've said before, is simple because we could use the stars and the horizon and do that at sunset or sunrise. So it's just some of those things that were required to understand. So some of the take-home messages here is this concept of latitude and longitude and representing this round surface onto a flat plane became very important when they started circumnavigating the world. We needed accurate time, we needed to use the stars, we needed to understand the stars in relation to the horizons. And that meant we were allowed to, or could, travel across the world with certainty. In the first part of the webinar, I've given you a background to navigation and some of the factors that need to be taken into account when traveling across the globe. I've introduced the concept of latitude and longitude as a way to locate a place on the Earth's surface. With the advancement in technologies such as global navigation satellite systems or GPS, we have been able to improve the approximation of the globe, and this has improved the accuracy of measurement, mapping, and navigation. In the second part of the webinar, I will discuss how we describe the shape and size of the Earth and how it impacts its mapping.